Okay, the second subtopic is calorimetry. The third one is called as kinetic theory of gases, laws of thermodynamics. And the last one is called as heat transfer. So today we'll be looking at thermal expansion and calorimetry. Right, somebody? Cool. Thermal expansion. Whenever we have a linear object, okay, of length L naught, original length L naught, of original length L naught, whenever we have an object, and if we heat it, okay, we supply heat to this rod. Let us assume that this is a metal rod. Then this rod will expand. This is the extra length that comes because of heating the rod. So this additional length is called as delta L. So the new length of the rod will be given as simply L is equal to L naught plus delta L. Agreed? Right. And delta L, as it so empirically turns out to be, delta L has the value L naught alpha delta theta. I'll explain every term. L naught is original length. Alpha is coefficient of linear expansion. And delta theta is change in temperature, which can also be negative. Okay, so now we substitute delta L as L naught alpha delta theta. It is an empirical relation. This is what we observe. We observe this. Cool. So after we substitute it over here, what we get is this is L naught plus L naught alpha delta theta is equal to L naught 1 plus alpha delta theta. Okay, अल्फा का यूनिट है 1 अपॉन टेम्परेचर. That's it. Okay, yeah. Now continuing from this equation over here, we also can write this equation as L minus L naught is equal to L naught alpha delta theta, or L minus L naught upon L naught is equal to alpha delta theta. L minus L naught is delta L is equal to delta L upon L naught, and this is the law of linear expansion. Okay, let's move on to new page now. Two-dimensional expansion. In two-dimensional expansion, we talk about planar bodies, bodies that can be said to lie in a plane. Like for example, a sheet. of metal. This lies in a plane, right? So in this sheet of metal, this has L naught length and this has B naught breadth, right? Length and breadth are L naught and B naught. Agreed? So each and every linear dimension is going to expand according to our earlier result. This is how linear dimensions expand, okay, when heated. So in a sheet, each and every dimension is going to expand linearly. There are two dimensions. So this L naught is going to become, yeah, each dimension is going to expand linearly. That's correct. This L naught is going to become L naught into 1 plus alpha delta theta. And this B is going to become, B naught is going to become B naught into 1 plus alpha delta theta again. Yes, that's correct. And usually speaking, alpha is small, very small. And so is delta theta. We don't look at like temperature changes from 0 to 100 degrees Celsius. Usually delta theta is small, but even if it is not small, alpha usually is very small. So in analysis, we can ignore alpha square. In analysis, we can ignore alpha square and higher powers of alpha. Right? Yeah. So let us see now what happens. Let us analyze. So initial area A naught was equal to how much? L naught B naught? Simple. Final area A is going to be equal to LB, which is L naught 1 plus alpha delta theta B naught 1 plus alpha delta theta. Okay, so this one expanding gives us L naught B naught 1 plus 2 alpha delta theta plus alpha square delta theta square. You will get it after multiplying the brackets. You will observe that this is nothing but 1 plus alpha delta theta the whole square. Of course, like we have said, this term we will ignore as per this logic over here. We'll ignore the alpha square term. So what we shall be left with is A naught 1 plus 2 alpha delta theta. This 2 alpha over here is called as beta. 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 A naught 1 plus beta delta theta, where beta is equal to 2 alpha. Similarly, if we look at volume expansion, and let us say draw a diagram of a cube or a rectangular parallelepiped that expands along three directions, again what we are bound to get is V is equal to V naught 1 plus 3 alpha delta theta, which is equal to V naught 1 plus gamma delta theta. You are invited to verify this yourself. Yes, all three dimensions will expand linearly. Perfect. Perfect. And those things we will ignore. Higher powers of alpha we are ignoring, right? So gamma is equal to 3 alpha. Gamma is equal to 3 alpha, right? And beta is equal to 2 alpha. Okay. Yeah, let us move on to the next concept, and that involves applications of what we have learned till now, right? Hmm. So these are the applications of thermal expansion. Okay, the first application is density variation. What is density given as? Density rho is equal to mass upon volume. Now if something is heated, what remains the same? Mass remains the same, right? But volume changes. And how is volume going to change? So if something is heated, delta dash or rho nu, not delta, this is rho. So rho nu is going to be equal to what? M upon, not delta V, V nu basically, right? Delta theta. Let's go over this one more time. Applications of thermal expansion. We are starting with density variation. Density is given as mass upon volume, right? So new density is given as mass upon new volume. Simple. Mass remains the same even if temperature increases and things expand. Mass remains the same. Mass doesn't increase or decrease, right? So new volume shall be given by V 1 plus gamma delta theta, right? Gamma is the coefficient of volume expansion, correct? So this is the exact expression, and mass upon volume is original old density. So this is like old density upon 1 plus gamma delta theta. कुछ नहीं, mass upon volume को I have substituted rho. I have substituted mass upon volume as rho. Over this one more time. Applications of thermal expansion. We are starting with density variation. Density is given as mass upon volume, right? So new density is given as mass upon new volume. Simple. Mass remains the same even if temperature increases and things expand. Mass remains the same. Mass doesn't increase or decrease, right? So new volume shall be given by V 1 plus gamma delta theta, right? Gamma is the coefficient of volume expansion, correct? So this is the exact expression, and mass upon volume is original old density. So this is like old density upon 1 plus gamma delta theta. कुछ नहीं, mass upon volume को I have substituted rho. I have substituted mass upon volume as rho. That's it. Just check it out. Yeah, so this entire volume is new volume, but new volume has been expressed in terms of old volume. So new volume is old volume into 1 plus gamma delta theta, and mass upon old volume is original density rho. So this is the exact expression that we get. Rho nu is equal to rho upon 1 plus gamma delta theta. Now this is the exact expression. Exact. We want new density in terms of old density. This is what we want. But now using binomial theorem, we can approximate this expression. This comes out to be rho 1 plus gamma delta theta inverse. And since gamma is very small compared to 1, this comes out to be rho 1 minus gamma delta theta. So you get an approximate expression for new density. Rho old, you can say 1 minus gamma delta theta. So this is an approximate expression. Approximate expression valid when? Valid if 1 is greater than gamma. Okay, and this is an exact expression. So this is density variation for you. The second concept or second application of thermal expansion is upthrust variation. Upthrust. Okay, so what is upthrust? Upthrust, we have seen in fluid mechanics, is basically the buoyant force. Okay, and we have seen that the buoyant force is given as volume immersed, volume of solid immersed into density of liquid into G effective acceleration. Yeah, all these terms have one special subscript associated with them. Volume of the solid immersed into density of liquid into G effective is the upthrust essentially. Okay, we are talking about here there is a liquid in which some solid is immersed and is floating. So volume immersed is this volume. This is the volume immersed. Liquid has a density rho L, solid has a density rho S. Naturally, right now rho S is less than rho L. That is the reason why solid is floating. Okay, G is the acceleration due to gravity. Fine, you're happy with this? Yeah. So tell me, out of these three, parameters, when we heat the entire system, what changes out of these three? Volume changes, density changes, or not? Of course, no? We have seen density variation right now. So both these things change. Okay. See now what I'm going to write. Upthrust nu or FB dash is equal to volume nu into density of liquid nu into G effective, right? But volume nu is what? Volume old into 1 plus gamma of solid, because volume of solid is changing, into delta theta. Change in temperature is delta theta. And density of liquid nu is given by the exact expression here, which is density of liquid old upon 1 plus gamma liquid delta theta into G effective. Yeah, because density of liquid is changing when we heat the liquid. That's correct. Solid ka density changes, but right now in our expression of upthrust, density of solid is it's not involved. Density of solid term is not involved in our upthrust expression. That is why density of solid is not taken into consideration. Right. So dividing equation 2 by equation 1. We get FV dash. FV is not Facebook. It's upthrust. Upthrust new is upon upthrust old is equal to, actually all that remains is 1 plus gamma solid delta theta upon 1 plus gamma liquid delta theta, and this gives you an exact expression. This right here is an exact expression of the new upthrust. Yeah, density gets cancelled, volume gets cancelled. Yeah, original density is getting cancelled, no? Not the new density. New density term has remained over here. New density term involves these two terms which have remained. Original density was cancelled. Just like here, mass upon volume was cancelled, no? Towards the left hand side, this mass and this volume was cancelled. Just like that. Okay, so this is the exact expression, as we like to call it. This is the exact. Okay, again, without going into details, I can use binomial theorem to approximate this expression, and I'll get the approximate expression as upthrust new is equal to upthrust old into 1 plus gamma solid minus gamma liquid delta theta. So this is the approximate expression. You can take it up as an exercise in binomial theorem expansion. Okay, for any rational index, particularly negative integer index, to understand how this approximation has come about. You have to use binomial theorem. So we have done 2 applications now of thermal expansion. So we'll move on to the third application, and the third application is period of a pendulum. Okay, period of a simple pendulum. Yeah, that's perfectly correct. We have found out the period of a simple pendulum in SHM, but here what we are going to check is how does the period vary when we heat or cool the pendulum. So when temperature changes, how does the period vary? This is what we are going to see. Okay. So this angle over here is theta, and the simple pendulum is happily oscillating, right? Why do we keep drawing diagrams all the time while doing everything? The reason for, yeah, forces and free body diagrams. The reason for that is physics can't be done without diagrams. We have to imagine, right? Okay. So what is the period of a simple pendulum given as? T is equal to 2 pi under root L by G. That's correct. Okay. So in the formula of a simple pendulum, what is the thing or what are the things that will vary when temperature changes? Can you tell? Only L will vary, right? So new time period will be 2 pi under root of L nu upon G. That's correct. 2 pi under root of L nu upon G. Okay. So abhi new time period upon old time period will be given as under root of L nu upon L. This is simple enough to understand. But what is L nu given as? According to linear expansion, what is L nu given as? Okay, here the assumption is that this L of the pendulum, okay, is made out of some material that expands after heating. So L is equal to L nu is equal to original L into 1 plus alpha delta theta. Perfect. So that will imply T nu upon T is equal to under root of L 1 plus alpha delta theta upon L, which is 1 plus alpha delta theta raised to half. Agreed. So with binomial theorem expansion again, time period new upon time period old is equal to, let me put it as T old everywhere, okay, is equal to 1 plus half alpha delta theta. Perfectly correct, Sam. Good. Good. So here we also see key T new minus T old upon T old is equal to half alpha delta theta. Now this is called as fractional change in time period, or this is delta T by T. Okay. Fine. Good. So what is the significance of this fractional change in time period? Let us say what is the period. Let us say the period of a pendulum is 10 seconds. Let us assume a pendulum that has a period of 10 seconds. Okay. So in one oscillation, when the pendulum oscillates like this once, okay, goes here and then goes back here. In one oscillation of the pendulum, how much time does the pendulum gain or lose? First of all, we need to understand that when the length increases, time period is going to increase, right? If time period is increasing, then instead of 10 seconds, let us say the pendulum is oscillating with 11 seconds. So what is the change in time period? 1 second, no? Correct. So in each cycle, the change in time period is 1 second. Okay. Let us say delta t is equal to 1 and t naught is equal to 10 seconds. So how much time does the pendulum lose in one oscillation? 1 second it has lost. So how much will it lose in, let's say, 100 oscillations? 100 seconds, no? But 100 oscillations correspond to 10 seconds into 100, that is 1000 seconds, right? 100 oscillations correspond to 100 time periods. Correct. 100 oscillations correspond to 100 time periods, because one time when it will oscillate, one time period will be over, no? One time period में, yeah, 2 minutes. You stand here. Okay, so in one oscillation, 10 seconds is required for it to carry one oscillation. So how many seconds are required for it to carry 100 oscillations? So 1000 seconds are required for it to carry out 100 oscillations. And we have seen in 100 oscillations it loses 100 seconds. We have seen earlier, because in one oscillation it loses 1 second. So 100 oscillations may it loses 100 seconds. Actually 1000 plus 100. So instead of, no, plus, it will carry out 1000 oscillations in 1100 seconds. It will carry out 1000 oscillations in 1100 seconds. So error in measurement is 100 seconds. See, for the original pendulum, in how much time should it carry out 1000 oscillations or 100 oscillations? 100 T naught, no? For one oscillation, T naught is required. So for 100 oscillations, how much is required? 100 into T naught is required. But because of this error, one oscillation was carried out in how many seconds? No, one oscillation was carried out in 11 seconds, because of 1 second error. So error in one oscillation is equal to 1 second. So total error in 100 oscillations is how much? 100 seconds. So now instead of carrying out 100 oscillations in 100 T naught seconds, it will carry out 100 oscillations in 100 T naught plus 100 seconds, no? T naught की value थी 10 second. So that I just substituted, no? 100 into 10 plus 100 is equal to 1100 seconds. Correct? So error is 100 seconds. So after 100 oscillations, the pendulum is telling us a wrong calculation of time by 100 seconds. Got it? It is telling us wrong calculation of time by 100 seconds. So that brings us to the concept of how much time is gained or lost in n oscillations. So in n oscillations, delta t by t into n time is gained or lost. Okay, that is what we did now. Delta t was 1 here, t was 10 into n was 100. Okay, so this much time is gained or lost in 100 oscillations. Fine. This is the time gained or lost in 100 oscillations. This is fractional time gained or lost in 100 oscillations. This is in fraction. If we convert it into, this is fraction, no? This is delta t by t ray is equal to 100. So what is total delta t? 100 t, ना? So t कितना है? और ये 10 आया है अभी हमें, 100 नहीं आया है, 10 आया है ना ये? हाँ, तो t कितना है? 10. तो 10 into 10 100. ठीक है, हाँ कॉल. अरे ओके, फाइन, कॉल कॉल. Okay, scale reading. So in scale reading, there is basically a linear object, okay, and there is a scale. Fine, no? This is the scale, you can say. Let me draw it like this. Is this part. This is the linear object.
स्केल के ऊपर है.
स्केल के ऊपर नहीं है मतलब scale has been placed against the linear object, man. Don't be angry on the scale. It's a good scale. Camlin. No. Yeah, okay. Camlin steel ruler. Now you are laughing at the scale. It's coming now. It's coming. Fine. So this here is a steel ruler. Now let us see what we have here. Listen, Sam. This is a rod whose initial length was L0. Okay. After we heat this thing, both the scale and the rod is also made of a substance that after heating expands. Okay. So what we do get is the new length of the rod is L0 1 plus
क्या हो गया?
alpha delta theta.
खराब हो गया.
Shh. L0 1 plus alpha delta theta. Okay. At 1 unit on the scale, the length of 1 unit on the scale was what? Initially it was 1 unit, right? So 1 unit on the scale, nu after expansion is going to be equal to 1 plus alpha scale delta theta. This is for the rod. This is one unit nu. See, 1 unit is distance between two points that have a measurement of 1. Right?
So
1 unit nu. New value of 1 unit. This is 1 unit. 1 unit on the scale. New value of 1 unit is equal to old value of 1 unit. This is length, you can say. These are lengths. These are lengths. Is equal to old value of 1 unit into 1 plus alpha scale delta theta. And new value of length of rod is equal to old value into 1 plus alpha rod delta theta. Make sense to you? Okay, good. Now, new measurement is going to be what? New measurement shall be what? Length of rod, that is new length, upon ln upon new unit, no? New length of 1 unit, right? This is going to be new length measured by the scale, and that is nothing but L0 upon 1. 1 has just value of 1 into 1 plus alpha rod delta theta upon 1 plus alpha scale delta theta. Fine. Okay, so new
न्यू लेंथ ऑफ 1 यूनिट में कुछ वैल्यू नहीं होगा क्या?
new length measured, yeah, it will have a value. The new value of 1 unit, it will have a value.
Like
But
what?
this bracket, like for example, earlier it was 1 centimeter. Now 1 unit is 1.1 centimeter. Earlier it was 10 mm. Now it is 11 mm.
इतना कम?
Yeah, expansion is small now. How much do you expect things to expand because of heat? So new length measured of the rod by the scale. Okay, let me write that also. Of the rod by the
Wait.
scale is equal to L naught into 1 plus alpha r.
एक मिनट. Sorry.
Yeah, it's correct. 1 plus alpha r delta theta
Wait. Alright.
upon 1 plus alpha scale delta theta. This is the exact expression. If we have to use binomial theorem to approximate it, it comes out to be L naught 1 plus alpha rod.
Minus.
Yes, alpha rod minus alpha scale delta theta. That's it. That's it. Okay, new application now. New page.
और कितने हैं?
Okay, expansion of materials with cavity or holes. Okay, for instance, let us say we have a disc over here and there is a hole in it. So in linear expansion, the thing that we need to understand is every dimension expands. See, logic will tell us that when the disc expands because of heat, no, the hole will actually shrink in size. Why? Because we will think that disc will expand, so hole will have to shrink, right, to make room for the disc to expand. In reality, the hole also expands when the disc expands, because distance between any 2 points now increases. So these 2 points also increases. Distance between these 2 points also increases. Yeah, I'll repeat. So our intuition will tell us that the hole needs to shrink when the disc expands. But actually, in reality, distance between any 2 points increases when the disc expands. Okay. The reason for that you can understand is something like this. Let us say there is a disc over here. There is a hole in the disc. Look at this piece now. This piece of metal or this piece of the disc, and look at this piece of the disc. When we expand, they both will try to come inside the hole. Agreed, no? They'll try to expand like this and come inside the hole, right? This will try to go here. This will try to go here. Yeah. So what our intuition says that the size of the hole should decrease. Okay. But now we will understand that there is also an adjacent piece of metal like this, like this, like this, like this, and so on. All of these are also trying to go inside. Now tell me, if there is a door and if there are two very fat people that are standing, they are so fat that only this is visible. Okay, and if they are trying to come inside at the same time, will they be able to come inside? Similarly, all these rods or bars of metal are trying to come inside the hole at the same time, right? So actually they will, face a reaction force and hence in fact expand in the backward direction. Are you understanding? And hence the rule that any 2 points expand. Okay, distance between any 2 points increases. Fine. Similarly, if there is, let us say there is a rectangular parallelepiped like this, okay, and there is a cavity somewhere in between, and if we expand this, all sides are going to increase and the cavity is also going to increase in size. The size of the cavity shall also increase. Understood? So this is a qualitative application. We don't have a formula for this as such. What you need to understand is that all dimensions increase in length, and hence holes or cavities inside substances that are expanding also increase in size. This is what you need to understand. Okay, the next application, okay, is that of additional stress induced because of expansion. So let us say these are two fixed rigid supports, okay, between which a rod is held like this, okay, and let us say now we heat the rod. So there is no room for the rod to expand now, anyway towards the right or the left. There is no room for the rod to expand, right? But what is delta L? Delta L is equal to, this is L naught, no, L naught 1 plus alpha delta theta. You should not forget. Delta L is L, yeah, oh right, correct. Delta L is just L naught alpha delta theta. What is delta L? Delta L is L naught alpha delta theta, and new length is equal to L naught 1 plus alpha delta theta. Perfect. So what additional length would have been required? This is the delta L additional length that would have been required, right? But we don't have that length. Okay, so this rod is experiencing strain, right? Strain. It is experiencing compressive force. It is experiencing compressive strain. Okay, so delta L that it experiences is L naught alpha delta theta. Therefore, delta L by L is equal to alpha delta theta, right? And delta L by L is nothing but the compressive strain. This is nothing but the compressive strain. That's it. So what will be the additional force exerted on the walls because of this compressive strain? For that we need to understand and recall that Young's modulus is F upon A given by Young's modulus is given by F upon A whole divided by delta L by L. And now we have to substitute this alpha delta theta over here. So Y is equal to F upon A upon alpha delta theta. Therefore F is equal to YA alpha delta theta. Simple. This is the additional force exerted on the walls because of thermal strain. That is it.